So hi everyone, welcome to this week's ZUCCMAP talk. So today we have Asaf with us, who's going to talk about he's in the mathematics masters, and he's going to talk about fast inverse square root algorithm and how it sped up a game. So I will leave the word to him.
Okay, hi everyone, I'm Asaf, and thank you all for coming. I'm going to talk about the fast inverse square root algorithm as it was implemented, actually got famous because of its implementation in the Quake III game, but it was actually also quite common beforehand. So first we want to talk about our motivation, and for this we have to go back to the 90s. We still have computers, but they're much slower than nowadays. Usually they didn't have GPUs like today. And also they didn't always have implementation for floating points. So a lot of implementations of floating points required using software emulations, which is much slower than integer operations. And also, the most important thing, that division is an operation that is much slower than multiplication. Sometimes it can be even 5 to 10 times slower. So we want to avoid as much division as we can. Okay, now our problem is that we have a lot of vectors, and we want to normalize them to get unique to length vectors. It is an extremely common operation for computer graphics, 3D games in general, because games have to run really fast, like 60 frames per second, sometimes a bit less, especially in the 90s. And we need to do it like sometimes millions of times per second, even more. We can find those operations in like normal vectors to surfaces, in reflections, in lightings. Here we have a good figure of surface normals. This is really common for computer games and also for generating this image. Also, the most important thing is that we sometimes prefer to compromise accuracy for speed, because our algorithm needs to run millions of times a second on a not so strong computer, because we are in the 90s. And we might compromise a bit the speed of the accuracy of our algorithm in order to be able to run the game much smoother compared to what can we do with a clever and accurate computation. Okay, as I said before, a division is 5 to 10 times slower than multiplication. Nowadays it is still true, but only up to factor 2, I think. And so we want to use the division as little times as possible. So we want to compute the inverse of our vector length and then multiply every element of the vector with the inverse of the vector length instead of divide. And also, if it is possible, we would like to compute the inverse of the vector length directly without going through computing the square root of all the squares of the values in the vector, because this way we can save some time. Okay. Now we are going to talk a bit about Quake III Arena, which was a game that was released by ID Software in 1999. ID Software is back then it was a very big company for games. It is mainly famous for Doom, which is a game that now can run on everything, I think. Yeah. Also, the source code for the engine of Quake III Arena was published in 2005. And Quake III Arena had very good graphics back then. And also, I think that this picture, I mean, using the projector, you don't see that much, but I think that the graphics is still quite good, not compared to modern games, but I think that if I played it now, it could be fine. It might not be the best possible graphics for a game, but I wouldn't suffer from the graphics that they made back then. Okay. And the Quake III arena game had a very clever but not original. They copied it from somewhere. They had an implementation for an inverse square root. And now we are going to talk a bit about the code that we see here. This is the implementation. The game was written in C, like most games back then, and also nowadays. And the implementation is not long, but quite vague. So if we look at the first 3 lines, they just define some constants and variables. In C, back then, you had to put all your variables at the top of the function. So you cannot declare variables after you started computing. This is still true for some C standards, but we are not going to talk that much about them. Then, yeah, they put in the variable x2 the number that we entered times half, which is dividing it by 2. Then they do some bit conversions from float to int. Very vague operations that the comment describes really well the first thought of everyone about this line. Then they turn the float back to the integer back to the float, do one computation that they plan to do twice, but they turned out that even one time is enough. So the algorithm is quite vague, and now we are going to talk about what they actually do. So first we are going to talk about Newton's method. I think that you have all seen it in numerical analysis class or a similar class. It is a very nice way to find roots of a function. And it works quite well provided you are really close to your root. In general, yeah, you take your value and move it a bit based on the value of the function and the value of the derivative. Okay, and now we are going to talk about our specific case that we want to find the square root of 1 over a. And in this time, we are going to use the function 1 over x squared minus a. Of course, f of 1 over square root of a is 0. So we are going to use this function. If we derive it once, we get minus 2 over x cubed. And what is really nice is that if we compute the iterative steps of Newton's method, we get that in the end, we don't have to do any division operation, because both in here, and here, we can actually multiply by 1/2 or use 3/2 as a constant. Okay, so now we are going to see what happens if we choose an OK starting point. So if our initial guess is 1/2, then the first iteration we get 5/8. Second iteration, yeah. The second iteration we get something that is quite close to 0.7. And the third iteration we get something that's really close to our value. But if we take a value that is not that good, like square root of 5 over a, as our initial guess, we get, after the first time, minus the square root of 5 over a, and if we do it twice, we get our initial guess. So we have to find a good way for finding our initial value, initial guess, because we cannot take a constant. 5 over a tends to 0 as we go to infinity. And taking 1 over a is okay, but requires a division that we want to avoid. And also, as we saw in the last slide, it might not be the best the best way, because we don't know how many iterations we'll need. Yeah, so if we look back at the code of Quake III Arena, we can see that they initially wanted to do 2 iterations, but after 1 iteration, they decided that their approximation is actually good enough for the game that they can actually stop. And now our question is, how do we make a very good initial guess? Yeah. And that's the answer, the weird 3 lines that we saw back in the code. Okay? And now we are going to understand what happens in those 3 or 4 lines. So first we have to talk a bit about floating point representations. We are going to talk about single precision, but everything works quite similar for every other representation of floating points. So in our case, we have 1 bit for sign, 8 bits for exponent, and 23 bits for mantissa. And our number is represented by -1 to the sign, which is 0 or 1, and 2 to the exponent -127, and 1 times 1 plus the mantissa over 2 to the 23. And using the fact that our mantissa is normalized, the representation is unique. There are also other kind of floating points that can be used using the standard, like denormalized, infinity, not a number, 0. But we are going to ignore those in this talk. And also we are going to ignore, of course, negative numbers because we don't have to calculate the inverse square root. And we are going to use B for 127 and L to 2 to the 23 as general constants. We can use other values for B and L, and everything will work quite the same. Okay, now if we want to convert a float to an int, we basically put the bits back to the order. The first 23 bits are the mantissa, then 8 bits for the exponent, and 1 bit for a sign. And if our number is 2 to the e minus b times 1 plus m over l, then we'll denote its integer representation by x tilde, which is e times l plus m. This is the number that you get if you put all the bits all together. Okay, now we are going to do some simple examples to make sure that we understood what happened. If we want to represent the number 1 as a float, then the exponent will be 0 plus the bias, which is 127. The mantissa, of course, is 0. And so the integer representation is 3f8 in decimal basis. Now we are going to do a bit more complicated example, which is 3.5. This time we have to normalize it first, so we get that 3.5 is 2 times 1 3/4. So the exponent is 2 plus the bias, which is 129, and the mantissa is going to be 3 times 2 to the 21, because we have to normalize, and the integer representation is what you see. Now, if we want to do a bit harder example, which is 1/3, which cannot be represented with any floating point representation precisely, we have to write the binary representation first, which is 0.01 alternating. And then we get that the exponent is -2, because we want to get 1 as our normalization. And every second bit is on. And this is our integer representation. Okay, now we are going to talk about what happens if we take logarithm of a floating point. So if we have our floating point that we have, we can try to take logarithm and apply some logarithm rules. And we get that logarithm of x is the exponent minus the bias, because we can just take them out, plus the logarithm of 1 plus the mantissa over L. but now we got a bit stuck. So we want to also see what can we do with the mantissa of, with the logarithm of the mantissa. So we can actually approximate the logarithm of 1 plus x as simply x. This is quite a good approximation. It actually works with as an identity at 0 and 1. We only talk about the logarithm of basis 2 here, because we are computer scientists. But in the middle, it is not the best optimizations that we can get, the best approximations that we can get. So we want to make our approximation a bit better. So we want to add a little sigma that we are going to find later. And this way we can get much better approximation of the logarithm of 1 plus x. And now back to the logarithm that we have. Now we can actually approximate our logarithm as e minus b plus m over l plus sigma, which is really nice because we have we have this sum of 4 different things, and everything is linear. And working with linear things is much easier than multiplying things and making everything much harder. So now we want to compute 1 over square root of a using the logarithm. And so first, if y is 1 over square root of a of x, we can take logarithm of both sides, and we get that the logarithm of y is minus half the logarithm of x. And now we can put everything that we got in our logarithm approximations that we got, and we got that the exponent of y minus the bias plus the mantissa of y over L plus sigma is roughly minus half the exponent of x minus the base plus the mantissa of L plus sigma. And now we can simplify and move everything sides, and we get on one side a linear equation with only the exponent of y and the mantissa of y, and the other side some constants and the exponent of x and the mantissa of x, which is really nice. And now if we remember our integer representation, we can put everything together, and we get that the integer representation of y as the 1 over square root of x is roughly 3/2 L times the bias minus sigma minus half of the integer representation of x. And this is exactly what happens in those 3 lines. Okay, now the question is, what is this magic number that no one understands? So actually this magic number, nothing is really special about it. It's just an approximation for sigma, for some sigma. We could choose other values for sigma and get some other magics. And we are going to talk a bit later about what magics we can put here. Okay. We can also do the same idea for general powers. We don't have to do it only for 1 over square root. You can do it also for square root, for x cubes, for x to the 100, if you really want, for x to the 99.5 for some reason. And we can do basically the same, and we get a very similar approximation in a general formula, which is nice. Okay. Now the question is, after we did everything, how fast is it? Because we did a lot of things to make our software much faster. So unfortunately, I don't have a computer from 25 years ago, so I had to check it on my 5-year-old computer, and I got the following results: that if I do no iterations of Newton Raphson, and I run it over all normalized floats. We don't have that many, almost 2 billion, so I can easily do it on my computer. It takes less than about half a second. If I add one iteration, which is the original implementation of the inverse square root, then it takes roughly 2 seconds. Another iteration almost doubles the time. And the naive implementation, which is just calculating 1 over square root using the library, takes around 3 seconds, which says that actually, even today, this implementation is faster by 50% than the naive implementation that everyone does. Okay. Actually, we can even improve the speed of the algorithm by taking the constant 1/2 out. And if we calculate half times xn times 3 minus a times xn squared, it actually runs 50% faster, and the overall runtime goes down from 2.1 seconds to 1.35 seconds. If someone has an explanation for it, I would be really happy to hear. I didn't find any. Do you have an explanation?
I was thinking maybe it's because we do the bits just once instead of twice. So when we're dividing like 3/2.
Yeah, but 3/2 is a constant already.
Oh yeah, sure.
I'm really curious about why did it happen, and also if this performance difference was also applicable 25 years ago when this algorithm was written, because now I cannot imply anything that I find on my processor about what happened 25 years ago. Intel changed a lot of things, and everything that happens under the hood is completely black magic. That I have no idea what happens. Is it because of better pipelines, because of better optimizations with microcode, better speculative execution? I don't know. Okay. Also, another thing that is interesting is that if it could also improve the speed 25 years ago, how did no one find it out? So, because they cared about speed much more than we care now. Okay, now another question is, how accurate is it? So instead of finding the ground truth from 1 over square root of x, we can use the equation that x times 1 over square root of x squared should be 1. So we can measure the error of this. And we have to take this square root for the values that we get, because we use the approximation twice. So we get double the error. And we are going to look for the maximum error that we get. So if we do with no iterations, we get about 3.5% maximal error, which I think is extremely close, but not enough for computer games and everything if you want the graphics to be smooth. After one iteration, we get less than 2 promille of an error, which is extremely good. If we do 2 iterations, we get almost vanishing error. And of course, the naive implementation, we get no error at all. And yeah.
The error does not depend on where we are evaluating this.
What do you mean? Like
it doesn't depend on the x. Like this is the.
I took the relative error, so
Oh, yeah.
it doesn't depend. But of course, yeah, it depends on the x.
I mean, in practice, at least.
No, I didn't. Actually, I didn't take. I just compute the maximal value of the error after the normalization. Yeah. Here, you normalize it. It should be 1. Yeah, but good question. So yeah, I can understand why the developers of Quake thought that less than 2 promille of an error is a very good approximation and a very good error that we can handle if we play computer games, especially back then. Okay. We can also improve the constants a bit. So if we change our magic number by a bit, we get the error, the maximal error goes down by a very little. So which raises the question, how did they find the original magic constant? And I think personally that the way that they found is trial and error. They didn't apply any analytic thing, and they just found a constant that they didn't really find a much better constant, and they just stopped. But also, if you remember, we have some constants in our Newton method. And maybe we can also improve those constants. And yeah, if you remember Newton's method iteration step, we have 1/2 times xn times 3 minus axn squared. But maybe we can find better constants than 1/2 and 3. So people actually looked for better constants, and the best constants that they find are those. They work a bit better. I think the error is going down by like 2.7 fold, which is nice. But also, this algorithm runs 20% slower on my computer. I don't know if it was also this much slower 25 years ago. And here I think that I actually know the reason, because multiplying by 1/2 is way faster than multiplying by an arbitrary float, because we just have to change the exponent by 1. So, and we don't have to deal with the mantissa. Okay. And now, yeah, unfortunately, Intel introduced a new opcode for calculating the even square root in 1999, which is the same year that the game came out. And this instruction is 4 times faster than the Quake implementation, and produces much smaller error, which is nice and gives us no reason to use the Quake's algorithm nowadays. Okay, and now the last thing that I want to discuss is that nowadays we have a lot of computation power. Like at ETH, we have like 250,000 servers at Euler. I don't know the exact numbers. I have in my pocket a phone that is much stronger than every computer in 1999, and I don't even have the top-tier phone. And yeah, it is even sometimes easier to double the number of servers or buying a stronger server instead of optimizing our code. In a lot of cases, you can just double, like buying a stronger server for $10,000 or even less, and optimizing in code requires some person to sit on it for 3 months. Maybe it will work, maybe it will not. And today we don't put a lot of effort into writing efficient code. We write more high-level code. We sometimes don't use the best methods available. We use some naive implementations instead of like using opcodes. For example, I don't think that I found a single library that actually uses the Intel opcode, which is interesting. OpenGL does not use it. Newer versions of Quake, I think, actually does. But not everyone uses the best opcodes that you can use. Or And in a lot of cases, you just use naive implementations that are not as fast as you can get with other methods. And it doesn't mean that this is the way that it should be. I think that in a lot of cases, we can optimize our codes, and we can save a lot of money and time, and giving a smoother experience for people. I think that I'm not sure that there is actually a good reason for computer games nowadays to consume like the all resources that the newest NVIDIA GPU can provide in order to provide the best quality picture that you can get. I think that maybe you can also use, with some optimization, some mid-tier GPU and get the same performance. And yeah, I would like to hear what you think about it. And thank you very much for listening and being here. If you have any questions, I'll be here. And yeah, thank you very much. Questions?
We have 15 minutes for questions. Otherwise, we can start the after early. One question here.
What's this new Intel implementation from 2009 as a Java in briefly?
So I don't know. The basic answer is I don't know. It might have changed over time. It might have even changed on my computer since I bought it, because Intel can actually update the processors that I have, like the microcode that runs under the hood, and they can actually change the implementation of the opcode. So the basic answer is I don't know. ARM also has its own opcode for the inverse square root. And unlike Intel, ARM does not manufacture their own processors, so they just write the standard, and other companies manufacture it. So you can actually read the pseudocode that they provide, and the pseudocode is basically 1 over square root. But I think it is still faster than other implementations because it runs on the hardware. So I think that even if you run on ARM computer and use the opcode, it will be faster than writing 1 over square root.
So most of the optimization comes from implementing it on hardware, or do you think they have some some breakthrough in terms of these constants or the number used or the magic part?
I don't think that I can answer the question without knowing the implementation. Yeah.
What's the significance of 1 over square root? Is it like the sticking point? Is it the thing that slows down graphics? Or is it just an example of one difficult computation that they managed to improve?
So I think it is a good example because people actually found a good implementation of it. But you can find other implementation, some other optimizations. And to be honest, I think that the reason that this implementation got really famous is not because of the fact that it is really clever, but because of this comment. I think this comment is the real reason why this implementation went famous. Also, it is worth noting that it was not an original implementation in the Quake III. Some people tried to trace back where this implementation come from, and I found a paper from 2003 that cites some form that is not available anymore, and I didn't find the web archive of it, so I don't know what happened. But every reference to this code before 2005 did not include this comment, so I think that this comment is actually original for the game code. And back to your question, I think that Yeah, 1/square root happens millions of times, if not more, every second in a computer game, and it has to be really fast. And if you can save, I don't know, 2 nanoseconds every time that you compute 1/square root, and you do it a million times, it is 20 milliseconds. And this means that you can increase your frame rate by a lot. Any other questions? Okay, thank you again.